this section ends uh, talking about the graphs of derivative functions. So now that we know that derivatives can be described as functions very similar to functions that we're already familiar with, we'll be able to we can think about their graphs. And well, what we're going to do, we're going to say, hey, if you're given the graph of f of x, could you give a sketch? So not a perfect graph, but as best we can do, can we get a sketch of the graph of the derivative? So we got two examples here. In part A, you can see the graph of f of x, and I haven't labeled the particular points, the x values where these things occur, the y value. That's not important. Just go ahead and kind of give yourself a sketch. It's supposed to be symmetrical, so wherever this occurs, down at the bottom there, that's kind of, there's some symmetry happening, and that's in the middle. We got this W shape. So take a moment and draw that. At the same time, I have drawn the corresponding xy plane down here, and this is where we're going to graph f prime. All right, so once you're ready, we're going to begin. Okay, how should we even start? Hey, remember that first example we did a little while ago, and we pointed out that the vertex of the parabola was when the derivative was equal to 0, right? We say there's a horizontal tangent line at that vertex. Well, the same thing really occurs here 3 times. Think of this location. What's going on with the tangent line there? Or more importantly, the slope of the tangent line. Isn't that slope 0 right here? And same thing over on this side, that slope is 0. And at the very top, that slope is 0. Okay, well, since the derivative this is going to be a graph of the slopes of the tangent lines. Graph, it's easy to get confused on what it is you're even graphing. A graph of the slopes of the tangents, we'll say. So the y values, if you will, are going to be those slopes. Let me say it. The slopes become the y values, the function values. Okay, so we said the slope is 0 here, 0 here, 0 here. So when we look here, all right, if the slope is 0, then that's my y value, 0. And that's true here at the middle as well, and on this point. So we know the derivative passes through 0 here, here, and here. But exactly how does it connect them? Does it kind of come up and then through, or maybe down or something? What exactly is the path? Okay, so we got to look back for more. What's going on with all of the tangent lines here in this first segment? Okay, so f of x is dropping, decreasing. So if we were to think of, these tangent lines here, what's going on? Or the slopes, aren't all of these slopes negative? M is less than 0. Negative slopes, right? So when we go to graph, we want negative y values. Negative slope means we graph a negative y value. Okay, let's do that in a moment. Come back over here. What's going on in this segment? If you thought of tangent lines there or anywhere along that path, aren't those all positive slopes? So then here between the two, we will have positive. Now we have to connect the 2 points. We just want to make sure we stay positive between them. So then over here, well, it's decreasing again. So all of these slopes are back to negative, less than 0. Then we hit 0, and then the slopes turn back to positive. So we've got negative, 0, positive, 0, negative, 0, positive. All right, negative. And here, this is kind of when it comes in that it's a sketch. It's negative, then it's positive, connecting the dots. Then it's negative, then it's back to positive, and there's a good sketch of f prime x. And you can, go as, as high up or as low. That's not really important. The fact that you've got the negative, positive, negative, positive, and the zeros, that's what we're looking for. Okay. Let's do a harder one. Here's a graph, f of x. Okay, so f of x, almost like it's like starting out of the origin and sort of got this sort of shape. Almost looks like square root there, but then we have the negative version as well. Okay, well, you may notice that f of x, if this is the sort of shape that we've got, it would have to be piecewise, and the two pieces are joined there at the origin. Do you remember what kind of point we call that? That's a cusp, right? So this will be good to have to graph a derivative function where there's a cusp. So it turns out here there's no place where the tangent line, the slope of the tangent line is 0. There's never a peak or a valley like, the vertex of a parabola. So what are we going to do with that? Well, we can't graph anything with 0, so we'll just have to go straight to the positive negativeness. So if you look at, the left side, what's going on with all the slopes of the tangent lines? These are negative, right? Over here, the slopes are positive. And we have that cusp there in the middle. Think about this. As we approach that cusp, aren't the slopes getting more and more negative, right? I mean, the slope here is more negative than the slope was back here, which is more negative than back right there. They're dropping. And as we go up, the slopes begin very positive, and then they get less positive because it starts to level off. So very positive and then less positive. So at the cusp, we went from a very negative slope immediately to a very positive slope. So that means in the derivative graph, we're going to go from a very negative value to a very positive value. Okay, here, let's graph it. So I've got my XY plane laid out. You can see my note here about the cusp. Okay, let's think this through. So it's a little bit negative, and then it's getting more negative. So it's kind of negative, but then it gets more negative. All right, and I'm going to put an open circle right there. Less negative, getting more negative. I just drew a straight line. This might kind of curve, a little bit. That's not so important. Less negative, more negative. Then it immediately becomes very positive. From very negative to very positive, and then it gets less positive as we move out. And I think it does make sense for this to kind of curve. It's probably kind of curving down, like getting less headed towards 0, but never reaching it in either direction. But that's not really what I'm looking for. More positive to less positive. Both of these have to be open circles because we don't have a derivative value at the cusp. So that's just an empty spot on the graph of our derivative. There's a big jump in the derivative graph at that cusp. And there you go. Okay, you'll see a a few examples of this in the homework. What's left? So I promised you guys a theorem. It's not nearly the one of like those huge heavy theorems like intermediate value theorem or squeeze theorem. But there is definitely a logical component to this, which is a good thing to wrestle with. Okay, so here it comes. If f of x is differentiable at a, then f of x is also continuous at a. All right, so we have this classic if-then sort of statement, fairly simple one, but let's think about it. So if you're differentiable, then you're continuous. I've got some notes here. If the derivative exists, then this is true, that the limit as you approach f of x is equal to f of a. And let me just ask, I know obviously you can't hear your responses. It'd be better if we were in class, but do you guys agree with that? Does this theorem make sense to you just based on the graphs and things that we've seen before? If the derivative exists, then the original function is continuous there. And remember what continuous means. There's no hole. There's no jump in the original function. There's no vertical asymptote. Right? Well, yeah, if there's no jump, right, and there's no hole, well, I guess we should look at it the other way. If it's differentiable, then that means there's a tangent line. So if there's a tangent line, there couldn't have been a jump, there couldn't have been a hole, there couldn't have been a vertical asymptote. Makes sense. Here's where people often have trouble. Like, maybe it seems like, yeah, we get it. What's the big deal? Here's where people have trouble. They try to reverse the if and the then. Okay, so what does that mean? So we call that the converse in logic when you reverse the two parts. So let me ask you this. Is the converse true? Can we switch them? Here we're saying if it's differentiable, then it's continuous. But is it true the other way? If it's continuous, can you conclude that it's differentiable? And it would seem at first like that's fine, right? If you're continuous, then you don't have a hole, you don't have a jump, you don't have a vertical asymptote. So sure, it would have to be, but actually that's not the case. The answer here is no. In fact, we already saw just recently in this very video, we saw a case where the original function was continuous, yet not differentiable. So if we were in class, it'd be like, where was it? What did we do today? And you'd have to think through, and maybe somebody would say, oh, it's just that very last example we did with the cusp, right? Let's look, right? So here, f of x is continuous, no problem. There's no hole, no jump, no asymptote, but there happens to be this sharp corner. It is continuous, but we got that edge right there. And so the derivative did not exist. So being continuous does not necessarily mean differentiable, although it does have to work the other way. So it turns out there's another situation where a function can be continuous but not differentiable. This was in a previous video. It was that vertical tangent line. If there's a vertical tangent line, then everything about that original function is continuous. You just can't take a derivative where the tangent line goes vertical because that'd be undefined. Okay. That is the end of chapter 2. Isn't that is incredible? In 1 week, we covered chapter 2. That is a record for me. So good job, you guys. Keep up the hard work. I will see you guys in the next video. I'm going to do a video on notation when it comes to finding derivatives with the definition of the derivative and all that and things that go with it. I'm going to speak to that, And then after that one, so watch that next, and then we'll go into chapter 3. Okay,